Performing elementary row operations on the system Ax equal to b can be viewed as applying certain linear transformations to both sides of the system. We'll illustrate the ideas on an example. Say we're looking at the system Ax equal to b, where A is given by this matrix here, b by this 3-tuple, and x is the 3-tuple of variables x1, x2, and x3. The system Ax equal to b written out in full is going to be the following. Let's first consider the operation of interchanging two rows. Suppose we interchange rows 1 and 3. Then the resulting system is the following. Now, consider the linear transformation T given as follows. So T takes the input tuple y1, y2, y3 and outputs y3, y2, y1. So what T does is it swaps the first and third entries of the input tuple. With this, we can express this system as T of Ax equals T of B. And if we apply T to both sides of this, that is, if we are looking at T of Ax equals T of B, what you get is in fact just Ax equal to B. Intuitively, this makes sense because swapping the first and third entries twice amounts to having done nothing. Now notice that we can rewrite T as follows. So T of y1, y2, y3 can be written as the matrix 0, 0, 1, 0, 1, 0, 1, 0, 0, followed by y1, y2, y3. And it's not difficult to check that this here indeed gives you this. So this is the matrix that represents the linear transformation T. And this matrix can be obtained from the identity matrix by interchanging rows 1 and 3. And in general, the matrix that represents the linear transformation that interchanges row I and row j can be obtained from interchanging row I and row j of the identity matrix. Say, for example, you're working on a system with 4 equations and you want to interchange rows 2 and 4. The matrix that represents the linear transformation that does that is the following. So you take the 4x4 identity matrix and row 4 becomes row 2 and row 2 becomes row 4. So this matrix here is the matrix corresponding to the elementary row operation of interchanging rows 2 and 4 in a system with 4 equations. Now let's look at the operation of adding a constant multiple of a row to another row. Suppose that we are adding 2 times row 1 to row 3. Performing this operation to the original system, what we get is this. Now consider the following linear transformation T. So it takes the input y1, y2, y3 and outputs y1, y2, and y3 plus 2 times y1. So T adds 2 times the first entry to the third entry. And therefore this system here can be written as T of Ax equals T of B. We can undo this operation by adding minus 2 times row 1 to row 3. And the linear transformation that does that is given by U, defined as follows. So U takes input y1, y2, y3 and outputs y1, y2, y3 minus 2 times y1. And one can easily check that U of T of Ax equals U of T of B is precisely Ax equal to B. And we can write T and U in matrix form. T can be written as follows, and U can be written as follows. In general, the matrix that represents the linear transformation that adds alpha times row I to row j can be obtained from adding alpha times row I to row j of the identity matrix. For example, if you're working with a system having 5 equations, and you want to add 3 times row 4 to row 2, The matrix that corresponds to that can be obtained by taking the 5 by 5 identity matrix and adding 3 times row 4 to row 2, resulting in this matrix. Finally, let's consider the operation of multiplying a row by a non-zero constant. Say we're multiplying row 2 of this system by a half. The resulting system is going to be this. And now consider the linear transformation T given as follows. So it takes the input tuple y1, y2, y3 and outputs y1, 1/2 y2, y3. Then this system here can be written as T of AX equals T of B. And this operation can be undone by multiplying the second row by 2. And the linear transformation that does exactly that is given by U of y1, y2, y3 equals y1 to y2, y3. So again, if you look at the system, U of T of AX equals U of T of B. That's precisely AX equal to B. And in general, the matrix that represents the linear transformation that multiplies row I by a non-zero constant can be obtained by multiplying row I of the identity matrix by the constant. So in summary, row reduction can be seen as a sequence of linear transformations applied to both sides of the system AX equal to B. Because the composition of linear transformations is itself a linear transformation, there's going to be a matrix M such that MAX equals MB is the result of the row reduction. We will see an example of computing this matrix M in the next video. Now, the matrices that correspond to the elementary row operations are called elementary matrices. These matrices are the building blocks for invertible matrices, which we will look at in the future. And so for this linear transformation, the elementary matrix will look like this. Finally, notice that each of the elementary row operations that we have performed on our example can be undone. What that means is that linear transformations corresponding to elementary row operations have inverses. This is a very important fact because it means that applying elementary row operations to a system of linear equations does not result in a gain or a loss of solutions. That explains why we can use row reduction to solve systems of linear equations, because each time we have a system that is equivalent to the original system.